In 8.7, we're going to talk about heat energy that is associated with reactions. So we talked about exothermic and endothermic reactions in a previous chapter. An exothermic emits heat energy, thermal energy. Exo is a prefix that means exit, like the exit signs above the door. What do? You go out. So heat leaves an exothermic reaction. Endo is like the word in, and that means that energy is coming in. So the amount of energy, thermal energy, that's emitted or absorbed is given the name enthalpy. And I'm not going to grill you on that word, but I'll be using the word, and so you need to understand it well enough that it doesn't mess you up when I say enthalpy. Enthalpy is a function, and it has to do with thermal energy being absorbed or released from a chemical reaction. Then it says under conditions of constant pressure. That's kind of our little fine print disclaimer, because if it's not under constant pressure, then it gets more complicated. So we're only going to deal with constant pressure. We'll save the other parts for 1A. Enthalpy of reaction has the symbol delta H subscript RXN. RXN is our chemistry abbreviation for reaction. Kind of like Xmas for Christmas, reaction. So enthalpy of reaction is delta H reaction. So when you see that, that's what that means. It's the amount of heat, which is thermal energy, that flows when a reaction occurs at constant pressure. Energy has a direction when it moves. So it can go out, it can come in. And so we have assigned energy flowing out of a system to have a negative sign, and energy coming in to have a positive sign. So you can think of your bank account or your wallet. When money leaves, when it's withdrawn, when it leaves your wallet, do you feel positive about that or negative? You have negative feelings about that. You'd like to keep the money, right? So energy leaving is like money leaving. It's negative. When all of a sudden you find out that someone has made a deposit into your account, you feel positive about that, right? Okay? It's dumb, but you'll remember it. So when energy comes into the system, when it comes into the reaction, that's a positive sign. There's a picture. We've seen a picture like this before. Here in this illustration, energy is higher at the top of the graph and lower at the bottom. So in an exothermic reaction, the reactants start out with more energy, and the products end up with less energy. Energy is conserved, and so it can't just disappear. This energy that was in the reactants is released to the surroundings, and the delta H for the reaction is negative. In an endothermic reaction, the reactants start with low energy, and the products end up with higher energy. And they have higher energy because they've absorbed energy from the system, from the surroundings. So they started with low energy, they started with not much money, and they received a bunch of money, and now they're wealthy. They've got higher energy. So in a chemical equation, we see it like this. Here's an example of an exothermic reaction, the combustion of methane, which is mostly what natural gas is. So when you burn 1 mole of methane, 802.3 kilojoules of thermal energy are released. So the negative sign there, that means the energy is going out. Another way, which your book doesn't go into but might help some of you understand it a little better, is you can also show it as part of the chemical reaction because heat is being produced. So you can also view that energy as a product of the reaction. This amount of energy relates specifically to the amounts expressed in the balanced chemical equation in terms of moles. So that amount of energy is released when 1 mole of methane is burned, when 2 moles of oxygen is reacted, when 2 moles of water is produced, when 1 mole of carbon dioxide is produced. So that amount pertains to each amount in the equation. Here's an yes, question?
Okay, but it's a negative. Why is it positive?
Why did I put it positive in the... Okay, because it's being produced. It's being produced and then it goes away. For delta H, the sign is negative because it's leaving the system. The energy was... Well, I can't say it wasn't there. But that energy was produced by that reaction, and so it shows up as a product. Okay? And here's the other sort of reaction, the endothermic reaction. Here delta H is positive because energy is coming in. And if we write the energy, darn it, if we write the energy of as part of the equation in this one, we'll get it as a reactant. So that's way off to the side, that's okay. If we were to express it as part of the reaction, it would show up as a reactant. Energy cannot be positive or negative. The sign is just telling us what direction the heat is going, because you can only measure heat flow. You can't measure the heat itself. It moves from one thing to another, and it comes back. When it's just in, well, you get into all kinds of complicated things about energy. It can go into different forms of energy, but you can't just measure heat. You measure the heat flow, and so it has to be going in a direction. Okay, so we have to say, well, it's either coming in or it's going out. When we express it as part of the reaction, then it's always going to show up as positive, because you can't have, just like you can't have negative mass, you can't have negative energy either. But this amount is for every 1 mole of this and 1 mole of that and 2 moles of this. If the coefficients here were doubled, then we would also have to double the amount of energy. Because if you burn a match, you get a little bit of energy, right? If you burn an entire orchard of dead trees, do you get more heat energy coming off? Yeah. You can drive by one of those burns in your car and you can actually feel the heat on the window. It's like, oh my goodness. I kind of wonder, maybe the valley is responsible for global warming. No, it isn't. But, that can't be good for the air quality either. Side issue. Okay. The amount of heat depends on the amount of stuff, right? That makes sense? So this is specified to correspond to molar amounts in the equation. So let's do some examples. Or maybe not. Maybe we'll talk about it some more. Forgot about this slide. So the amount of heat absorbed or emitted depends on the amounts. Kind of said that. The delta heat of reaction is specified for the stoichiometric amounts of the reaction as written. The magnitude tells us how much is being transferred. The sign tells us what direction it's going in. So here's the equation for the combustion of propane. A mole of propane will react with 5 moles of oxygen to form 3 moles of carbon dioxide and 4 moles of water. And in that process, 2,044 kilojoules of heat energy are released. So we can form conversion factors from this information, just like we did with mole ratios. So we can say that there's 2,044 kilojoules of energy for every 1 mole of propane. Or we could say we're going to get 4 moles of water produced for every 2,044 kilojoules of energy released. Or we could say if we use up 5 moles of oxygen, we're going to release 2,044 kilojoules of heat energy. Get the idea? You can take that enthalpy and use any of the molar amounts in that equation and form a conversion factor. So then we can answer questions like, well, if I burned 2 moles of propane, how much energy would be released? Well, then we're going to need to use this conversion factor right here. If I get this much for every 1 mole, then I would multiply by the number of moles, and that would tell me how much heat energy was released. So let's do an example. Ammonia reacts with oxygen according to this reaction, and for every 4 moles of ammonia that reacts, we get 906 kilojoules of energy being released. It says calculate the heat in kilojoules associated with the complete reaction of 155 grams of ammonia. So again, this is stoichiometry with a twist. We're going to take these the number and the question and put them under the terms in the equation. So 155 grams of ammonia is what they gave us. And the question is, how much heat? So over here, this is the heat term, delta H. So this is question mark. And they specified that they want the units to be kilojoules. Well, our path, our map has been grams to moles to moles to grams. So we're given a mass here. That's good. Are we asked for a mass, though? No. Can we relate kilojoules of energy to moles of ammonia? We can, because we can relate kilojoules to any of those, to moles of ammonia, to moles of oxygen, to moles of nitrogen monoxide, or moles of water. We can choose whichever one we need. So for a problem like this, you're going to go grams to moles and then directly to kilojoules. It's like a shortcut. You actually don't have to go through the muddy swamp. There's a little path that goes around the side and get where you want. I was reading Dora again last night. I could tell you about some of the very, very weird things in that Dora story. Anyway, beside the point. So we're going to go grams to moles to kilojoules. So these problems end up being a little bit easier because there's only 2 steps instead of 3. So 155 grams of ammonia, we're going to convert to moles of ammonia, and then we're going to convert to kilojoules. Units first. Moles of ammonia down here to cancel that one. Grams of ammonia over here to cancel that one. The kilojoules to mole conversion we get from the equation that we were given. The amount of kilojoules, delta H, is minus 906. So we write minus 906. That negative is just telling us that that's going out. It's the amount of heat leaving. It's like money. Can you have negative $5? Not really. there are $5 bills. There are no negative $5 bills. But we understand what that means. That means that I owe someone $5, but you can't really have negative money. Oh, let me tell that to the government. Sorry. Shut my mouth. Okay, NH3. We need the molar mass so we can convert grams to moles. So nitrogen is 14.01 plus 3 times the mass of hydrogen, and that comes out to be 17.034. Again, with this 7 that looks like a 2. There we go, 17.034 grams of ammonia is equal to 1 mole of ammonia. I forgot something in that last term, didn't I? 906 kilojoules of energy is released for how many moles of ammonia? For 4. I forgot to put the 4 there. It's important. So I calculated the molar mass of ammonia, and so I'm going to put that in over here, 17.034. Then we use the calculator, 155 divided by 17.034 times negative 906 divided by 4, and we come up with minus 206 kilojoules. How many significant figures should that answer have? It should only have 3. The enthalpy was three significant figures. The mass was 3 significant figures. So we need to chop this off at the 6. There were some other numbers. The calculator said 0.025, blah, blah, blah. We're rounding a number to the left of the decimal point, which is where people get into trouble. You can't round 2061 to 206. If you like to do that, then I'll do some money transactions with you and make a bundle on you. So we're going to put that in scientific notation first, and you don't have to write that out. I'm just writing it out for illustration. So that's that number in scientific notation. Now when I round it, I can just chop it off and I don't get into trouble with changing the value. I don't have room down there, so I'm going to write it up here. Minus 2.06 times 10 to the third kilojoules. That's the answer. That's the amount of heat associated with the reaction of 155 grams of ammonia. Now you can imagine that this might be a useful sort of calculation in industry. Like, even in cars, well, if you burn this much gasoline, how much energy, how much heat is released? I'm trying to do this thing and I need to know how much energy is released. So these are very practical sorts of calculations. Questions? I think we have one more. What mass of butane in grams is necessary to produce 1.5 times 10 to the third kilojoules of heat? And 2 questions. What mass of carbon dioxide is produced? Well, let's organize our information. They're saying that we have 1.5 times 10 to the third kilojoules of heat. And they're asking what mass of butane. That's the first question. Let's ignore the second question for right now. So our map, our path was grams to moles to grams. Well, this time we're ending up at grams, right? They're asking how many grams. We're ending up there. But are we starting with grams? No, we're starting with something else. We're starting with kilojoules. Can we convert kilojoules into moles of something? Yes, because we know that there are 2,658 kilojoules of energy released for every 4 moles of butane that burn. So we can convert kilojoules to moles. And so in our path, again, we're taking a shortcut, and we're going to jump in here. So Dora got airlifted in and got dropped off in the muddy swamp, and now she just has to go to the snowy mountains. Right? It's a shortcut. It's easier. So the path tells us we're going to start with kilojoules. So we write down, we've got 1.5 times 10 to the third kilojoules, and we're going to convert to moles of the thing we're interested in. With these calculations, we don't have to do a mole to mole because the kilojoules can be converted to moles of anything in that equation. And then we're going to go to grams of C4H10. Yeah, that's really messy. Sorry. So we divide by moles of butane, so they cancel out. And then here we're going to divide by kilojoules, so they cancel out. We put the units in first, then we go looking for numbers. The kilojoules and moles one is from the equation. There's a 4 in front of the C4H10, so we put a 4 there. The delta H is minus 2658. Now, what about that number? What mass of butane to produce that amount of heat? Would that be a positive or a negative if we're producing heat? So this really, if we're going to be careful with our negative signs, that should be negative because that's the amount of heat leaving, that's being given off by burning, right? So I'm going to make sure I've got negative 1.5 times 10 to the third. It's off the edge of the screen. I did write it, though. You can watch the video. Then grams of butane. So we need to calculate that. 4 times 12.01 plus 10 times 1.008. $58.12 grams of C4H10 equals 1 mole. Again, do not use the coefficient 4 and multiply everything. Can you do it and get the correct answer? Yes, if you remember to put a 4 in the denominator, but then you're multiplying by 4 and for no good reason. It just makes more work, and every time you have to push buttons on your calculator is another opportunity to make a mistake. Or for the calculator to not respond when you press the button, which it does sometimes. That's the mass of 1 mole. So we have 1.5, that's negative, EE3, times 4 divided by 2658 as a negative number, times 58.12 equals, and I get 131.2 basically grams. How many sig figs should our answer have? 2. The number we started with was that amount of heat, 1.5 times 10 to the third. That only had 2 significant figures. And so that's going to limit our answer. And here we have another situation where we're rounding off to a digit that's to the left of the decimal place. So that's going to be 1.3 times 10 to the 2 grams of butane. When we're careful with those negative signs, they work out okay. Can you end up having a negative mass? Only in science fiction. So if you come up with a negative mass, it just means you were sloppy with your signs. So that's one of the questions. The other question is what mass of carbon dioxide is produced? So our second question is mass of carbon dioxide produced. Well, how do we do this? It's the same basic idea. Kilojoules to moles to grams. We can apply this to any of these compounds in this reaction. Where am I going to put this? It's a problem. We don't need to see the question anymore. So we're going to go kilojoules to moles to grams. So again, minus 1.5 times 10 to the third kilojoules of energy. We're going to convert that to moles of CO2 this time. And then we're going to convert to grams of CO2. So we stick our units in there so that they all cancel out so beautifully. The first term comes from the balanced chemical equation. For every 4 moles of CO2, we get 2658 kilojoules of energy. And we need the molar mass of CO2, which is 12.01 plus 2 times 16. Do not multiply by 4. 44.01 grams of CO2 is equal to 1 mole. So we've got 44.01 to 1 mole. Times 4 times, I did this one wrong yesterday, 99. I learned from my mistakes. I forgot to multiply by 4. 99 grams of CO2. Again, we're rounding to 2 sig figs. Any questions? Anybody wondering what about that 13 halves? That's not a good way to balance an equation, is it? Well, it's balanced, it's just not pretty. If we clear the 2 and make it all beautiful, let's just see what happens if we do that. If we multiply by 2, then we get 13 here, and this becomes an 8, and this becomes an 8, and this becomes a 10, and then we have to multiply this by 2. If we multiply the coefficients by 2, we have to multiply the enthalpy by 2. So a word about mastering chemistry. Q is energy. They didn't really use that in this chapter, but Q is energy or heat. So in mastering chemistry, they're often asking for you for the absolute the absolute value of the heat. And they use words to indicate that the heat was given off or absorbed. And so read those questions carefully. It's okay to list it as a positive number when we're specifying in our words that this amount of energy was given off. If we're not using any words to describe which direction it's going, then we need to pay attention to the sign. There's some stuff about Bunsen burners, and this is some kind of interesting pictures. This is a Bunsen burner that's not getting enough oxygen, doesn't have enough air. It affects the quality of the flame. You may be wondering, why are we talking about Bunsen burners all of a sudden? This is a combustion reaction of methane, and we were just learning how to calculate the heat given off. If we add a little more air, we see that the flame gets bluer. This is an optimum flame, with a nice cone in it. When you give it too much air, now the flame begins to float above the burner. And this sort of flame is the one that goes out because of the draft in here. So when your burner is just, you'll light it and it just goes out all the time. Crank the air down a little bit so that the flame is coming straight out of the burner like this. And then there are some review slides here. Don't ask me for a review sheet because this is it right here. Those are the chemical skills. Those are the sorts of things you should be able to do.